So if we want to think about circular motion, we have to kind of start off with circles and triangles, and that's often how we start off. So I'll just do a little quick review of triangles. So if we have a triangle here, I'm going to draw straight lines because this could get messy. So I have this triangle here. Oh, that's much better. Alright, and we can say that it has some angle here that I denote by the Greek symbol theta. And I'm going to call this length here the adjacent length. This here is the opposite. And this here is the hypotenuse. Alright, so you just have to remember that. I always remember the opposite because it's opposite the angle. It's opposite the two lines that represent the that have the angle. So you just have to memorize that, really. And we can write functions that describe for us the relationship between the length of these different sides and the angle. Okay, so that's really important. And so we can write that a function called sine of the angle is going to equal the opposite over the hypotenuse. That cosine is equal to the adjacent divided by the hypotenuse, and that tan of theta is equal to the opposite over the adjacent. And so basically these functions were developed in order to describe for us how the angle of a right-angled triangle, this has to be right-angled, relates with the lengths of the sides. And you'll find that all triangles can be decomposed into a whole bunch of right-angled triangles, and that makes solving the length of another side very easy. Something you can, kind of a mnemonic that can help you to memorize this is I usually remember SOHCAHTOA, where it's sine of opposite over hypotenuse. Cosine is the adjacent over hypotenuse, and tan is the opposite over the adjacent. And so that kind of makes sense. So let's now put this into a circle. And now we get to describe something in the x and the y plane when we shove this triangle inside of the circle. Oh, I can't draw circles very well on this tablet. Oh, there we go. That's not too bad. So we can describe a point on this circle using this triangle here. Okay, because we know we can draw a line down here, and so this becomes a right angled triangle. We consider this the angle, and a positive angle is in this direction, so this is positive theta. We consider this length here sine of theta, and you usually have to times it by the hypotenuse, and so that's going to equal r. And I'm just going to call the hypotenuse r for now. You can kind of think of this as the radius of the circle, and then this here is r cos of theta. And I'll just prove this because this isn't always clear. So let's work out the length of this side here. So the length of this side, we can go SOHCAHTOA, so it's going to be sine of the angle is going to be equal to the adjacent, which is what we want to find out, which is the y length, the adjacent divided by the hypotenuse, which is r. And you can do the same for the bottom. Cos of theta is equal to x over r, and then if you times both sides by r, you get out that the y component of this is r sine theta, and the x component of this is r cos theta. So that just describes for us the length of the different components. And so what I'm going to do is I'm going to denote this as r sub x, and this one up here as equal to r sub y. Alright, so this is the y component, and this here is the x component of this. We'll call it a vector for now. I'll introduce what vectors are a little bit later, but this is a little bit of a teaser. So this here is a vector which I can decompose into two different parts. So the next thing I'll just teach you quickly in this video is degrees and radians. So degrees was thought up because they wanted some sort of unit in order to describe angles, and they just chose a number that you can divide through by anything. So 360 is a really nice number because you can divide it by lots of different things, but there are things that you can't do with it, and it's kind of an arbitrary unit of measure that we kind of came up with. Because it made the maths easier for us, but it's not. There's nothing intrinsic about it with the circle. There's nothing about it that is particularly special. However, if we have radians was developed because it's a natural unit that comes out of a circle. So if you have a circle that's radius is 1, then its perimeter, its circumference, is going to equal 2 pi. And so we come up with this new unit, which is kind of fundamental. It comes right from the circle itself, and so basically a circle has 2 pi radians around the outside, and this makes more sense because you're actually dealing with something which is specific to a circle, and it's not just some number that we made up. So we have to, let's say we want to convert 20 degrees into radians. And we can just use the unit conversion rules that we learnt earlier. So that's going to make this really nice and easy. So what we do is we write the degrees in terms of radians, because we've got degrees over here, the unit is degrees, and we're trying to turn it into radians, so we have to write degrees in terms of radians. So we've got 360 degrees in 2 pi radians, and I'll just denote that as rad. That's the unit, no pun intended. So if I want to times 20 degrees by some conversion factor, I'm going to want to flip this, and that's going to cancel out degrees on the bottom and top, and it's going to leave us with radians on the top, which is what we want. So we're going to go 20 degrees times 2 pi divided by 360 degrees, and you'll see the degrees and the degrees cancels. We can go 20 times 2, and that's 40 pi divided by 360, and that gives us pi over 9 radians.